So, let's say you want to implement your favorite board game in code. The rules for most games are pretty straightforward to think about how to turn it into lines of code, regardless of the language. But at some point, you're going to come up against randomness. There'll be dice or cards or some other random element that you need to write code for. The problem you run into is code is deterministic. You write step-by-step instructions. That's what an algorithm is. How do you have an algorithm for randomness? Well, the first thing that came to my mind was using a mathematical constant that has random-like digits to it. And of course, I'm thinking about the most famous mathematical constant, pi, the ratio of the circumference of a circle to its diameter. 3.14159.265 and so on. In fact, the digits go on forever. Well, if we want to use the digits of pi as the dice rolls of our game, we don't want to use the 0s, 7, 8s, or 9 because our dice are assumed to go 1 through 6. We can get rid of those. And what we're left with is 3, 1, 4, 5, 2, 6, 5, and so on. Just the digits of pi in the range 1 through 6. And these can be the dice rolls of our game. To understand if these rolls are fair or not, one thing we can look at is the distribution. Does every number have an about equal chance of showing up? So here we can count the ones, and in the first 100 digit of pi, we have 1, 2, 3, 4, 5, 6, 7, 8 different ones. And we can plot that on our distribution graph. And we can do the same for 2s and 3s and so on. And we see we get this distribution. A few more 2s and 3s, and we see 1s and 5s, but that would happen with natural dice rolls anyway. Not every number comes up the same amount of times, especially with only a few number of rolls. Well, what if we go more rolls? What if we take 1,000 digits of pi? What we see here is it's a much more even distribution, just like we'd expect from real dice. And finally, at 10,000 digits of pi, we have a very even distribution of numbers across all 6 digits that we're looking at, really closely approximating what we'd expect to see from rolling a real dice 10,000 times. So that's it. Problem solved. No, the problem's not solved. We need to know how to compute the digits of pi for our code. And this is hard, especially if you want to do it quickly. That's a problem for another video. Today, we want to find some alternate method, something that's a fast and easy algorithm to give us random-looking digits. So what we need is a simple arithmetical method of producing a random sequence of numbers. To do this, we can turn to John von Neumann, a 20th century scientific legend, commonly thought of as the smartest person who ever lived. What does he say about this? Anyone who considers arithmetical methods of producing random digits is, of course, in a state of sin. Oh, he seems to be putting us off this whole endeavor. Fear not, he also produced the first and one of the most famous algorithms for doing this, called the middle square method, or the middle square algorithm. So von Neumann himself tells us something we can do, which is to take our first number, or it's called the seed number, square it to get a new number, and take the middle digits, and that middle digit will be the next number. And we just repeat and repeat again. So let's see what von Neumann's middle square algorithm looks like in code. So here's some Python code. It takes in our initial number called the seed, squares it, appends some zeros, so it'll be exactly 8 digits long, then takes the middle digits 2 through 6 and adds it to our list. We have to pick a number to start the process with. Here we'll take 1,111, and we start our middle square process. We take the number, square it, resulting in 1,234,321, 1, 2, 3, 4, 3, 2, 1. And now we put a 0 in the front, so it's exactly 8 digits, take the middle 4 digits, and that gives us our new number, 2,343, and we add that to our list of random numbers. We can go through the same process again and get 4,896, and again, and again, and again, each time getting new numbers, adding to our list of random numbers. So von Neumann's strategy works. Let's try it with a different seed, with a different initial number. Be patriotic, and I chose 1776. We know what to do, square it, take the middle digits. It gives us 1541, then 3746, 325, and so on and so on. We get a nice long marching string of more and more numbers that seem to be very random from what we can tell. Well, 24 is maybe the first hint that maybe something's about to go wrong. Let's take 24. We can square it. We get 576. Add the zeros, take the middle 4 digits, and we're left with the number 5. Well, 5 doesn't seem so bad, but if you think about the next step, you can realize a problem we're about to run into. If we take 5, square it to get 25, add our zeros and take the middle 4 digits, now we have 0. And 0 is a real issue. 0 squared is 0, and we just add another 0. And 0 squared is 0 again, and 0 again, and 0 again. We're stuck in a loop of zeros. The process has come to a dead end. And this isn't just a problem with 1776. If we go back to our first example, 1111, yes, we have many, many, many digits of great random numbers. But right here, when we get to 4096, we can see problems start to develop again. 4096 led to 9600, 1600, 5600. We're seeing a pattern of a lot of kind of double zeros at the end. All numbers are all hundreds. If we go 5600, square it, take the middle digits, we get 3600. In fact, you should pause and try to prove to yourself that once the last 2 digits are 0, they're going to stay 0 forever. That's not the only problem, though. 3600, well, we apply the method. 3600 squared is 12,960,000. We take the middle 4 digits and we get 9600. 9600, why is that an issue? Well, it's already in our list of random numbers. We've cycled back onto ourselves. 9600 will lead to 1600, 5600, 3600, and eventually 9600 again. So we've hit our first big issue with random number generation, which is cycles. We knew the numbers weren't really going to be random. They were pseudo-random. They're created by an algorithm. But we don't want to get the same 1 or 2 or 3 or 4 numbers again and again. When we had 0, 0 led back to 0, led back to 0. It's a cycle of just one number. When we had 9600, it led to 1600, then to 5600, then to 3600, and back to 9600. It's a cycle of 4. We can't avoid cycles. Every pseudo-random number generator of this form is going to have a cycle in some sense. A good pseudo-random number generator will have very large cycles that spans many different numbers before it starts repeating. And that's what brings us to linear congruential generators, LCG for short. These are popular random number generators that can give us very large cycles if tuned correctly. So how do you make an LCG? Well, if we start looking at the core of our middle squared algorithm, the squaring is you take the previous number and you multiply it by itself, and then we're going to pull out the middle few digits. Well, instead of pulling out the middle few digits, a different way of making sure the numbers are a fixed size is by taking the last few digits. And you can do this by dividing the number by, let's say, 1,000, and taking the remainder after you divide by 1,000, that'll be the last 3 digits. And more generally, this is called the modulus operator, where you divide by some number m and take the remainder. And we're going to indicate this with the %sign m. So we're not going to take the middle digits, we're going to take the last digits using the modulus operator, and we're not going to square the number, we're going to multiply it by an arbitrary parameter a. So now we have 2 free parameters to play with to design our random number generator, a and m. We're going to add a third term, c, which we add each time before we take the modulus, and you'll see in a minute why this is so important. This is it. This is our random number generator. If we bring back our middle square code, we can see how much simpler actually an LCG random number generator is. It's essentially just one equation. We take the last number, multiply by a, add c, take mod m, and that's the next number. Multiply by a, add c, take mod m, and that's the next number, so on and so on. As simple as LCG is, you still have to be careful. It's very easy to mess this up by not choosing the right values of a, c, or m. As an example, let's imagine we chose c of 0, so we're just going to multiply and mod and not add anything. What can go wrong here? Well, it depends on your seed. Imagine that initial seed value was 0. What's going to happen? 0 times 37 is 0, mod 1,000 is 0, and we're stuck in the 0 cycle already. We only have one unique number that comes out of a random number generator. It's just all zeros. How do we fix this? Well, as a start, don't use c of 0. If we use c of 1, we'll have a diversity of random numbers, and in this case, we get 200 different numbers before we start cycling again. You also have to be careful with your choice of a. If we chose a of 30 rather than 37, we're going to get the numbers 1, 31, and then we get stuck at 931, leading back to 931. We only got 3 unique numbers before getting stuck in a cycle. We don't want that. One way we can try to avoid generating these short cycles is to make sure A and M don't share common factors. Right now, 30 and 1,000 both share a common factor of 10. So if we switch A to be 11, instead of having a cycle where we get stuck after 3 numbers, we have hundreds of numbers. We have 500 numbers before we run into a cycle. And if we picked 101 instead of 11, we now get through all 1,000 numbers before we cycle. Another thing to consider when choosing your values is it's often popular to have m that's a power of 2. For example, we could have used 1024 instead of 1,000, and this lets us just take the last digits of the binary representation to quickly compute the modulo operator. And this leads to still 1,024 unique digits before we cycle. So let's get back to our motivating example of virtual dice. Let's throw 100 random dice. We can do that by first calling our LCG code with the good values of A, C, and M that we saw a second ago, and get 100 values out of it. Now, these values aren't going to be dice rolls, they'll be numbers from 0 to 1024. To turn them into the range 1 through 6, we have to process the numbers a little bit. Let's zoom in on the first few examples to see what's going on. The first thing we do is divide by the maximum value we could get, which is 1024. Next, we're going to take all of these values, multiply by 6, and then round up so everything's in the range 1 to 6. And now we have our dice rolls. So are these good random digits? Let's find out. We can test these like before by looking at the distribution of digits. When we plot them against each other, we see it's not perfectly even. We have a lot of 5s and not so many 4s. But we haven't taken so many numbers, so maybe that's to be expected. Just like real dice, we're not going to see the same number every time, and it won't be even unless we take lots of dice rolls. So what if we do 200 instead of 100 rolls? Everything starts to flatten out a little bit. And at 1024, at over 1,000 rolls, everything is basically perfectly flat. We're seeing all of the numbers 1 through 6 an equal amount of time. So why is LCG so important? It's built into the C standard library, and a lot of software that runs on C is very important. Things like operating systems that run your computers and phones have LCG built into them. We're seeing here the source code for Linux, Apple's OS, BSD, all of them have built in an LCG random number generator. They're all using this value of A, C of 12, 1, 2, 3, 4, 5, and M of 2 to the 31. Otherwise, it's an LCG, just like we've seen here. And it has all of the same promises and pitfalls that LCGs can have. Speaking of pitfalls, there are massive issues you can run into if you're not careful when designing random number generators. We've already seen the first major issue, that if you choose A, C, and M poorly, your numbers aren't random at all. They're just caught in very small cycles. There's an even bigger problem. Fundamentally, if somebody else knows the values of A, C, and M that you're using, if they can find just one number that you generate from your random number sequence, they can run the sequence themselves and know all the numbers in the future. That's not very random at all. Lastly, there's a lot of hidden structure that's built into numbers that come out of the LCG method. We've actually already seen some evidence of this. When we showed the graph for 1024 dice, the results were too uniform, too evenly spread between the numbers. This is unavoidable because we intentionally choose an LCG that has large cycles where every potential number shows up exactly once, making the result exactly uniform. Real dice are going to have more variance than this random number sequence. This can be a big problem depending on your application, and in future videos, we'll show even better approaches that avoid all 3 pitfalls.